everyone, thank you so much for coming to this video. So in this video we're going to be going over moments. So please review the videos on Newton's law of motions as these may come into use for this video. So the learning objectives for today is to be able to calculate a moment of a force, to be able to understand that when a rigid body is in equilibrium the resultant moment is zero, and to be able to use moments in simple static context. So like always, there's going to be timestamps in the description of the video, so feel free to skip to any parts you want to. But let's get started. So a moment, that is just a turning effect of a force around a point. So if you're asked to calculate a moment, all you have to do is, that's just equal to your force times your perpendicular distance from the force's line of action. So you could either have anti-clockwise moments or clockwise moments. Clockwise moments is just clockwise turning effect of a force around a point, and anti-clockwise is the anti-clockwise turning effect of a force around a point, and that means the sum of the moments, that's just your anti-clockwise moments plus your clockwise moments. So as always, your force times your perpendicular distance from the force's line of action. So just remember that. So let's say, for example, you had something like this with your point A, and you want to find your moments around your point A. You have one force which is 2 newtons, which is 1 meters away from your point A, and another force which is 5 newtons, which is 2 meters away from your point A. So to calculate the moments, first, if you want to calculate your clockwise moments, that is quite simple, because that would just be equal to your force. So your force is just perpendicular, so that's just 2 times your distance, so that's just 1, so that's just equal to 2 newtons meters. So now if we were to calculate our anti-clockwise, so this is a little bit more tricky as your line of action is not perpendicular to A because your force is at an angle of 60 degrees. So to calculate your anti-clockwise moments, there are 2 ways you could approach this. You could either find your perpendicular distance from your line of action, or you could find your perpendicular force from the line of action. So if you were to start off with finding the perpendicular distance, which is just this D here, you could write that your anti-clockwise moment, that's just equal to your force, which is just 5, times this distance. You have a right angle triangle here, so this D would just be equal to 2 sine 60, and if you plug that in your calculator, that would just be equal to 5 root 3 Newton meters. Or alternatively, if you were to calculate the perpendicular force, so you could draw a right angle, so you want to find this F here, so you have another right angle triangle with this angle being 60. So then you could also say your anti-clockwise moment is just your force here, which is just 5 sine 60, times your distance, which is just 2. So that would also be equal to 5 root 3 Newton meters. So it's the same thing. You could do either one, it doesn't matter, as long as you're working either perpendicular distance or force your line of action, if your force is acting at an angle to your line of action. So now to find your total moment, you just want to add it up together. So taking your clockwise as positive to be 2, taking your anti-clockwise as negative, so minus 5 root 3. And if you plug that into calculator, that's just 6.66 Newton meter, and that's your answer to this question. So your sum of moments, that's just your clockwise, take that as positive, and then you subtract your anti-clockwise moment from that to find your total moment. So that's just how you can calculate a moment of a force. So just remember that you are always dealing with a perpendicular distance or perpendicular force. So if your force is given to you at an angle, then you need to calculate one of those before you can use your formula here. So now let's move on to our second learning objective. So if we move on to our second learning objective, that if a rigid body is in equilibrium, the resultant moment is 0. So this is just saying that if your system is in equilibrium, then your anti-clockwise moments will be equal to your clockwise moments about any point. So you could just apply this fact to any question you may get. And you could use this to work out different aspects of moments, so either your force or your perpendicular distance. So let's see how we could use this with this example question here. So we have a seesaw AB of length 4 meters is supported by a pivot at its center. Child C of mass 30 kilograms sits at the end of A. Child D of mass 45 kilograms sits X meters from the center of the seesaw, and the seesaw rests horizontally in equilibrium. So the seesaw is modeled as a uniform rod, and we want to find the value of X. So like any question with mechanics, we just want to label on anything we can onto our diagram first. So we know that it's 4 meters, it's got that already. And now we just want to label that our child C is sitting on end A. So we'd have a downward force here of just 30G. And then we have child D of mass 45 sits X meters from the center of the seesaw. So if we have child D sitting here at 45G, and this bit here is X. And it's saying that our seesaw is resting horizontally in equilibrium. So that means our clockwise moments is going to have to equal our anti-clockwise moments. And we want to find the value of X. So the first thing we want to do is work out our clockwise moments, and that's for this child D. So our seesaw would go that way. So we could just say that our clockwise moment is just equal to our force, which is 45G, times our perpendicular distance, which is just times X. So now if we work out our anti-clockwise moment, so that's for the child at A, we can say that our force, which is just 30G, that's just equal to 30G times our distance. So because this is at the center, the distance to A, that's just times 2. So now because we know it's an equilibrium, these will equal each other. So we could just say that 60G is just equal to 45GX. We could cancel out our G's. So our X is just equal to 60 over 45, which is just 4 over 3 meters. And that's the answer to this question. So when you're working with equilibrium moments, you just want to find your clockwise moments and find your anti-clockwise and just equal them together if they're in equilibrium to find different components, either your force or your distance. So that's how that's everything you need to know for our second learning objective. So now let's move on to using moments in simple static contexts. So moving on to be able to use moments in simple static contexts. So there are some key definitions that you may need to use when applying this to this kind of question. So the first one is if you're asked, if the question mentions a uniform rod, then that means your weight is going to act at the center of your rod. If it's non-uniform, then you may need to be asked to find the center of the mass. And then the next one is point of tilting. So whenever a rod is resting on a support, then you'll always have your normal reaction force acting on the rod at that point where it's on your support. But then if your rod is at a point of tilting at a specific support, then your normal reactions for your other supports will be 0. You'll only have a normal reaction force for the support that is tilting on. So let's see how we can apply this to this example question here. Feel free to attempt it yourself if you want to. So we have a uniform rod AB has length 3 meters and mass 4 kilograms. The rod rests horizontally on 2 supports C and D, where AC equals 0.5 meters and AD equals 2 meters. So the first thing we want to do is find the magnitude of the reactions on the support at C and D. So if we start with part A, we want to find the magnitude of the reactions of the support at C and D. So if we label our reaction forces, these would be going upwards. So we'd have one here as RC and another one here as RD. And we have our weight, which is just 4G, acting in our centre of the rod because it's uniform. So the first thing we want to do is we just want to resolve vertically. And we know that because the rod is resting, it's in equilibrium. If we resolve vertically, this should equal to 0. So we could just say our upward forces, which is just RC plus RD, that will equal to our downward forces, so that would just be equal to 4G. So now we want to take moments. You could either take moments around about C or D, it doesn't matter. But let's just try take moments about C. So because again, we know that our rod is just resting, so that means we know that our clockwise moments is going to equal our anti-clockwise moments. So if we start with our clockwise moments, which would be from our weight, 4G, so we could just say our force is just 4G times our perpendicular distance, and because we know it's a uniform rod, then this weight is acting at the centre, so from A to 4G that will be 1.5. So that means that from C to our weight 4G, that would just be equal to 1. So 4G times 1, that's just equal to, now if we were to do our anti-clockwise moments, that would be from RD. So we could say that's equal to RD times our perpendicular distance from C to D. So that would just be equal to 2 minus 0.5. So that's just times 1.5. So now if you were to rearrange that, you'd get your RD is just equal to 8 over 3 G newtons. So that's what your reaction at D would be. So now just using this formula that we got when we were resolving vertically, we could just say our RC is just equal to 4G minus 8 over 3 GN. So that means your RC is just equal to 4 over 3 G newtons. So that's your answer to this question. So just to sum up what we did, we just resolved vertically to say that our RC plus RD is equal to 4G, and then we just took moments about C, recognizing that because it is in equilibrium, our anti-clockwise moments will equal our clockwise moments, and then we just, using that, we used our first equation that our resultant force was 0 to find our other reaction force. So now it's saying, we move on to part B, we're saying a block is now placed at B and the rod is on the point of tilting about D. So if we redraw our diagram, so we'd have A here, B here, we'd have a block is now at B, so we have a block here. And we want to find this weight here. And we would have we'll still have our same support C and D. We will still have our reaction force here as RC, still have RC, our weight will still be 4G, and our distances will still be the same. So because it's at the point of tilting about D, so that means that using this, because it's tilting at G, we'd have our reaction force at C that would now just be equal to 0. So now we can just use all this information to find the weight of the block. So we can do this just by taking moments about D. So again, using the fact that because it's resting, our anti-clockwise moments will equal our clockwise moments. So if we start by taking our clockwise moments, which will be from our W, so we could just say W, our force times our distance, which is just 1, is equal to our anti-clockwise moment, which would be from 4G, so our force is just 4G, times our distance, and this distance is just 0.5. So then if you solve this, you'd get your weight is just 2g newtons. So we take moments about d here, because we know that our RC equals 0 already, so we won't have to deal with any of the moments here. So then to not go through the whole hassle of trying to find out what RD is, if you just take your moments about D, you just don't have to deal with your RD. So it just means that we can solve our W with using any information that we have. So part C, lastly, we want to find the magnitude of the reaction at D. So now we want to find what our RD is, and we could just do this by resolving forces again, and because it's at rest, our resultant force will be 0. So if we resolve in the upward direction, we would say our RD, that's just equal to forces in the downward direction, which is just equal to 4g, plus our weight, which is just 2g. So that means our resultant force in RD, our reaction at D, that's just equal to 6g Newton. And that's answered this question. So that's one example of how you could use moments in a simple static context. The main takeaways that you should take from here is just that if anything is at rest, then you know that if you resolve vertically, then your resultant force will be 0. Also, if it's at rest, you know that your anti-clockwise moments will equal your clockwise moments. And just remember that if it's a uniform rod, then your weight will act to your centre. And if something's at the point of tilting, then that means there's only a reaction force at that support. The other supports, the reaction forces will cancel out to 0. So now let's move on to another example of a static context that you could get. So the last type of context that's quite common is using ladders. So we've got an example question here, an exam style question. Using what we've covered so far, try this question out for yourself and see if you can apply all these definitions that we've gone through to this question. So we have a uniform ladder AB of mass 20 kilograms and length 5 meters is at rest with one end A on rough horizontal ground and the other end B against a smooth vertical wall. The coefficient of friction between the ladder and the ground is 0.4. The ladder makes an angle 0 theta with the ground. So given that the ladder is on the point of slipping, the first part is we want to find the magnitude of the frictional force of the ground on the ladder. So like any mechanics questions, like always, we just want to label any forces we can on this diagram. So because we know that the mass of our ladder is 20 kilograms, and because it's uniform, it's going to be acting in the center of our ladder. So we could just label this weight as being 20g. And then we could just label this distance as being 2.5 meters because it's at the center. And we can label our whole ladder as being 5 meters. So now because we know that it's a rough horizontal ground at A, that means that there's going to be friction at A here. So that means that because it's at the point of slipping, if you think about a ladder like this, if it's slipping, it's going to slip that way. So friction always is in the opposite direction of the motion. So if the ladder is going to slip like that, your friction is going to be acting in this direction. So you'd have friction A. And like always, because there is a weight of the ladder, you're always going to have a reaction force from the ground onto the ladder. So you'd have RA something like this. And now if we move on for B, because it's a smooth vertical wall, there's not going to be any friction, so you don't have to worry about that. But there is going to be a normal reaction force acting from the wall onto the ladder. So it would be like this. So now that we've labelled any forces that we could deal with on this diagram, part A, we want to find the magnitude of the frictional force of the ground onto the ladder. Because we know our coefficient of friction, mu is 0.4, we know that and it's because it's at the point of slipping, then if you remember from our friction video, you could just say your F is equal to mu R. You could say your F of A is just equal to your mu times R of A. So if you resolve vertically, you know that you'd be able to find your R of A, because remember, if that's at rest, and then using Newton's third law of motion, every force has an equal and opposite direction. So we just want to resolve like in the vertical direction. So if we do that, we could just say that RA, that's going upwards, is just equal to our downward motion, which is just our weight. So RA is just equal to 20g. So now we can just plug everything into this formula. So we could say our friction, F of A, is just equal to our coefficient, our mu, 0.4 times 20g, which is just 8g newtons, and that's what our friction, the frictional force would be. So now part B, we want to find the value of theta to 1 decimal place. So in order to find the value of theta, we just want to see what we can actually do. So one thing that we can do is we can resolve horizontally, as we know our friction. So using our resolving vertically, as we found out at F of A, we'll be able to find our RB. So if we do that, we could say that we could just say that HG would just be equal to RB. So we know one thing. So now that we know our weight, we know distances, and we know RB, because everything's from A, we could use all of this to try, and we could take moments around A, and maybe that will help us find our angle. So let's try this, moments about A. So again, because our ladder is just at rest, it's in equilibrium, our anti-clockwise moments is going to equal our clockwise moments. So if we first try and take clockwise moments, so this will be from the weight of our ladder. So we could just, and because remember that whenever you're dealing with moments, you have to deal with perpendicular distances or forces. So the line of action will be this ladder. So we want to try and find our components of this force that is parallel and perpendicular. Because we're dealing with moments, we just want to find the perpendicular one. So our angle theta would be here. So we can find this so we know this perpendicular force will just be 20g cos theta. So then we could say our moments about A, our clockwise, is just 20g cos theta times our distance from A, so that's just 2.5. And that will be equal to our anti-clockwise moments. So again, we want to find our perpendicular force. So this would be our angle here. So we want this bit, which would be RB sine theta. So we can say that's equal to RB, which we find is 8g sine theta, times our distance from A, which is just B. So now, if we rearrange this, we could say that 50g cos theta is just equal to 40g sine theta. So if we rearrange this, we get 50g over 40g is just equal to sine theta over cos theta. So that just means 5 over 4. These would cancel out, which is equal to tan theta. And then theta would just be the inverse of tan of 5 over 4. And if you plug that into your calculator, that would just be equal to 51.3 degrees to 3 dp. And that's your answer to part B. So these moments questions, they have a lot of marks in your exams. They are quite difficult, but they mostly follow the same process, the same steps. So as long as you learn these steps, then you'll be able to apply that to any question you get. So what we did here, for part A to find the frictional force. That was just using your F equals mu r, and resolving vertically. You can find our RA and then just plug it in to find your friction. And then for part B, you wanted to notice that because they've given you distances and they've given you forces, then you know that you would be dealing with something to do with moments. And then because you could take moments about B, that's fine. But then if you see most of the distances make sense from A, because otherwise you'd be dealing with too much, you'd be dealing with friction, like resultant force would be too much if you're doing it from B. So you want to take your moments about A, as that will be more simple. And you just have to remember that because your ladder is at an angle, it's not everything your forces is not in your the direction of your line of action. So you need to find your perpendicular components of your two forces of your weight and your RB. And once you found your perpendicular components of the forces, you could just plug that into normal to your equation. Just remembering that because your ladder is in equilibrium, your clockwise moments is going to equal your anti-clockwise moments, and then we just solve that normally, normally algebraically, and then using some trigonometry. So yeah, as long as you remember these steps, just make sure you notice that if they have given you distances and forces, then you are using moments, and just remember these definitions that I've written on the side here, and you can just apply that to any question. That's everything. Thank you so much, everyone. Hope you found that useful, and you're now able to calculate moments for force and can apply this to solving simple static contexts. We went through two main types of problems you may get in your exam, involving ladders and also rods. But make sure you do a lot more practice questions and exam questions, as this is probably one of the hardest topics you're going to get in mechanics, as it pulls together all the different topics we've learned involving forces, Newton's law of motions, resolving forces. So make sure you really practice this properly, and the more questions you'll do, the better you'll get at it. You'll probably get the most marks with these types of questions, as they are the hardest. So make sure you do fully know how to do everything that I've covered in this video, and you do a lot of practice just to make sure you're fully comfortable with this topic.